Conservation Principles, System, and Environment. The most powerful concepts in science are called conservation principles. They allow us to solve problems without worrying too much about the details of a process. We just have to take a snapshot of a system, initially and finally. By comparing those two snapshots, we can learn a lot. So if our system is this traffic light here, we see it's green, and then after passing through yellow, it turns red. We actually don't care about the yellow part. We don't care about the electricity that goes into it. We don't care why it's doing it. We just want to know where it is in the beginning and where it is in the end. A good example is a bag of candy. If you know that there are 50 pieces of candy at the beginning, and you know that none of the pieces have been taken out or added, you know that there must be 50 pieces at the end. You can change the way you arrange them by moving them around, from an orderly state here to a pretty disordered state here. But you will still have 50 pieces. In that case, we would say that the number of pieces of candy is conserved. That is, we should always get the same amount, regardless of how they are arranged. We also have to be clear about the system that we're talking about. If we're talking about a specific type of candy, we can't suddenly start talking about a different type or a different bag of candy and expect to get the same answers. We must define the system whenever we use a conservation principle. But what is a system? And how does it help us solve physics problems? Let's discuss these two questions before we get back to conservation principles. First, why can we even solve physics problems? You've learned about forces in solving physics problems, but have you ever wondered how we can actually solve them? After all, every object we study is in some way affected by a lot of other objects. In fact, you could say that any object is affected by everything else in the universe. We know that the moon exerts a gravitational force on the Earth, so it must exert a force on every object on the Earth. Why then, when we work out the motion of a drop ball near the surface of the Earth, don't we need to take into account the effect of the moon's gravity? Or for that matter, the gravitational force from the sun and all the other planets? When we solve for the motion of a drop ball, we only consider the gravitational pull of the Earth because the Earth's gravitational force on the ball is so much bigger than the gravitational force of the moon and everything else on the ball that we can ignore everything but the ball and the Earth when solving the problem. So even though every object in the universe affects every other object in the universe, most of the effects on any one object are too tiny to care about. Often, we can just consider one object or a small number of objects and ignore everything else. To solve problems, we divide the universe between what we want to study and everything else. So here's what we want to study, and this is the rest of the universe. The piece of the universe that we study when we solve a specific problem is called the system. And earlier, the system would have been our bag of candy. A system may consist of one or more objects or amount of material in a region of space. We put an imaginary boundary or picture frame around the system. Everything else, some or all of the universe outside the system boundary, is called the environment. When our system is unaffected by anything in the environment, we call it a closed system. It's as if the system was in a universe by itself. Objects in it can't leave, no outside object can get in, and no outside forces affect anything in it. When a system can be affected by its environment, we call it an open system. While we focus on the objects in the system, they are affected by the environment. Objects might be able to leave. Outside objects might be able to come in. Some outside forces can affect the objects in the system. So back to the bag of candy, if the bag was unopened, it would be a closed system. If we rip it open, then objects can come in and out, it would be an open system. By separating the system from the environment, we can make a problem solvable. By defining an appropriate system, we can isolate the forces and the objects that are within the system from the forces and objects outside the system that are in the surrounding environment.